Alright, so in this video we're going to look at first an open loop control, and then we're going to look at closed loop control using proportional control. So the open loop, we're going to have a set point. My set point is going to just be 5 volts for each example that I'm going to do in this video. So I have 5 volts here, and I'm going to feed this out of my PLC. So I have my PLC here that's going to send out an analog output, okay, to my system. Now my system is the RLC circuit. So I have a resistor here, I have an inductor, and then I have a capacitor, okay? And so it's a series RLC circuit, and what I'm going to do is my output, my process parameter, is going to be the voltage across the capacitor. Okay. And then what I'm going to do is I'm going to apply proportional control. So I'm going to have a gain factor here, call it KP, which is going to be proportional control. So I'm going to feed back the voltage across my capacitor. I'm going to feed that back into my PLC. It's going to generate an error signal, which is the difference between the set point and my voltage across my capacitor. Multiply that times the gain, and then feed that into the system, this RLC circuit that I have down here. So that's what we're going to control. Now, I've already built the program and have it connected up and running here. And I'm just going to walk through some of the ladder logic. So notice that up here at rung 0, I have no contacts on the left-hand side. So this means this is going to happen every single scan. What we're going to do is we're going to read in the voltage across the capacitor. Every scan of the PLC, we're going to read in the voltage, which is coming into channel 0. So you see there it says local 4. Okay, so if we look at our tags here, I guess I'll go through the tags first. So I have my input coming in is the voltage across the capacitor, which is the channel 0 input of my analog card. Okay, so let's look at our analog card. This is the, we're using the fast analog card here for the Allen Bradley PLC. And I've got it, channel 0 is enabled, my input is enabled, and it's allowed to fluctuate between -10 to +10 volts using a 5 hertz filter and engineering units. Okay, I also have my output enabled, -10 to +10 volts, engineering units. And that's enabled there also. So that's my analog card. I'm using channel 0 and channel 1. Along with that, we of course have the switches on our trainer PLC here and our lights. So I have an amber light, a green light, a red light. I have a start and stop button, which I'm not really using right now. I have a selector switch, which I can select between either open loop or closed loop. And then I have a second selector switch with 4 settings, and I'm going, depending on which setting, that's going to set the gain of my PLC. And then now my input, when it comes in, is an integer, right? That's just the analog card is just reading in that voltage signal and converting it into an integer value, which is actually millivolts. So I'm going to convert that to a real value. Okay, so I'm going to have my voltage across my capacitor. I want that to be a real value, so I'm going to have to divide by 1,000 to make it a floating point value. My set point, I also want to be a floating point value in case I want to set it to, say, 3.75 volts or something like that. Right now, in this video, I'm going to use 5 volts, so you could argue I could have made it an integer, but you want to have the flexibility to make it a fraction, so you need to make sure it's a value of real. Your error definitely is going to need to be a value of real. And then the control signal we're going to send out is going to be multiplied by the gain, so we definitely want to make that a real value. And then when we send it out, then it's going to go out as an integer. So when we send it out, it's going to go out as millivolts. So the control out is actually in volts for this example. And then we multiply it by 1,000 to get millivolts, so we can actually send it out the channel 0 of the analog card output. All right, so then here I just have my gains. I'm going to have 0.5 or 0.5, half a gain of 1/2, however you want to look at that, a gain of 1, gain of 2, and a gain of 5. So I've set all these up as real values. So now over here you can see that I preset my gain to be 0.5. I have a gain 0.5, which I set to 0.5. I have a gain 1, which I set to 1, a gain 2, and a gain 5. All right, and I'm going to use ladder logic then to select them using these selector contacts on my selector switch. Okay. And my set point, right now I've got my set point just set to 5. Okay, so here is my logic. I have, the first thing I do is have my 4-position selector switch to select whether the gain is going to be 1/2 or 0.5 gain, gain of 1, a gain of 2, or gain of 5. Okay, so what it's doing is just doing a move of that gain tag into my KP tag, which is my proportional gain that I'm actually going to use in the controller. So by using this, I can quickly switch my gain by flipping the selector switch. Okay. Additionally, I'm going to move out a 0 if the selector switch is in the center. So right now the selector switch is to the right, and so this is not active. But if I put it in the center now, what I'm doing is I'm outputting my control as a 0. So that basically means I'm just outputting 0 volts, which will discharge the capacitor of the RLC circuit. Okay, and then if I switch it over to the left, that will be open loop control. And if I switch it to the right, that will be closed loop control, where I calculate my control is KP times the error. That's just proportional control. And I also turn on the green light of the PLC, which I won't have in the camera, so you won't actually see that. But the green light comes on. I might show that a little bit later. All right, and then I actually have a couple other rungs here that just use a greater than, so that if the voltage across the capacitor gets above 3 volts, the amber light comes on. If it gets above 5 volts, the white light will come on. All right, and then the last thing I'm doing then is, before I send my output, I'm going to scale it again into millivolts as an integer. So remember, the actual output through the output card is an integer, but control out is a float, and so I have to, control out is in volts, control out integer is millivolts, so I actually have to multiply by 1,000 to output that. So that is my control system here. Okay, so let's look at our program. First thing we want to do is look at our tags. Okay, so I have several tags. I have I have some relay light tags set up, pre-wired lights on the PLC trainer. I have a amber, green, red light, and a white light down here. So those are all already pre-configured and set. Then I have a start and stop button, which I'm not really going to use. I have a 3-position selector switch, so it goes to the left for bit 2, or to the right for bit 3. In the center, they're both 0. And then I have the 4-position selector switch, and what I'm going to do is I'm going to select my gain by selecting that switch. So these are just Boolean switch settings. And then I have gains here that'll actually, all I have to do is flip the switch to change my gain. So my gain is KP, this proportional gain, but I'm going to set that gain by using using these tags here and the selector switch. So I can make a quick changes just by flipping the switch. Okay. My input is coming in. Remember, the input is the voltage across the capacitor. That's my process parameter or my process variable of the system I want to measure. So it's an RLC circuit, and I want to measure this the voltage across the capacitor. But when it comes in, it's going to be in millivolts. Okay, so let's look at, and the same for my control out, it's going to be in millivolts. Let's look at my configuration of my card. So my card, my input 0, channel 0 is enabled. It's set to a voltage range, minus 10 volts to plus 10 volts, and filter of 5 hertz to kind of keep the noise low. And it's set to engineering units. Okay, so engineering units means that 10 volts was actually going to be 10,000 millivolts. Okay, and the same for the output. I have it enabled. It doesn't have a filter setting, but it's set to minus 10 to plus 10 engineering units. So those are the configurations of my input card. So when we come back and look at the tags, we see that channel 0 input, I for input, is going to be in millivolts. That's going to be the voltage across the capacitor in millivolts. And then we're going to have the voltage out, which was our control signal out, which will also be in millivolts. Those are the actual outputs. Then I have a real variable that's going to be the voltage across my capacitor in just volts. So I'll be dividing by 1,000. That's my scaling for this. And then I have my control out will also have to be scaled before it goes out. I have my set point, which is a real value, so I can put in, values of like 3.75 or, fractional values if I want. And my error definitely has to be of real value because it might have some floating points in there. Okay. And then here's my actual gain that I'm going to use in the closed loop control. All right, so now we will look at our so now we'll look at the actual ladder logic. Okay, so when we look at the actual ladder logic here, the very first rung is going to happen after we read the inputs. So the inputs come into the various tags, and of course the most important one here is the voltage across the capacitor. And again, the input comes in as millivolts as an integer value. So I'm going to divide that millivolts by 1,000 into a floating point destination, a real number destination, which is going to be my voltage across the capacitor in volts. Right? This is the input. V cap in is in millivolts, and it's an integer. So I need to make that a floating point value. I need to do that every scan, so there's no contacts on the left here. We're going to do that no matter what. Okay. I'm also going to calculate my error. My error is the set point minus the V cap. I actually used a compute statement here, but I could have actually used just the ordinary math subtraction block for that either way. But I'm calculating my error signal here, which is the difference between the two. Then I have 4 rungs, which are my 4-position selector switch, which are simply going to move my gain into the a value of gain into the actual KP gain value. So the gain will either be half of 1/2, right? 0.5 or 1/2, or a gain of 1, or a gain of 2, or a gain of 5. So I've preset those gains in here. I went ahead and preset those gains ahead of time. I also preset my set point to be 5 so that I can just flip a switch and have it output a response. Okay. All right, so here is the center position of the 3-position selector switch when both of these are open. And so I'm going to move 0 in. So to basically just output nothing or put the system at rest, or which will discharge any voltage on the capacitor, I put the left selector switch in the center position. And then if I flip it to the left position, what I'm going to do is simply move my set point out. So I'm simply going to output 5 volts. And I'll also enable the red light on the PLC. On the other hand, if I move the selector switch to the right, it's going to do the closed loop control, or proportional control. So remember, proportional control, you just multiply that gain value Kp times your error. And so when I do that, I'll also have it turn on the green light. All right, so once we've done that, I have a couple of rungs here that just use a greater than block to turn on the amber or the white light. So if my voltage across my capacitor exceeds, 3 volts, it'll turn on the amber light. If it exceeds 5 volts, the white light will also come on. And that just gives me an indication of how much voltage is on that capacitor without actually having to try to read a scope or get a voltmeter or something like that. I can just visually see the light and have an indication of how high the voltage is on the capacitor. And then the very last thing we do, and again, there's nothing on the left side here. We do this every time we send out our control signal, and our control signal is the calculated control value times 1,000 to convert it back into millivolts. So control out is in volts, multiply it by 1,000 makes it millivolts, which matches the engineering settings that I have set up for my output. One other thing to look at on the output settings, we need to make sure that your voltage can swing. So right now it's my lowest that I'll allow out is 0 volts. My highest is 10.5 volts. All right, so those are the settings there for the scope. So let's just take a look here as we as I activate it some here. So what I'm going to do is I'm going to take my scope, put it into single mode to trigger, so it's ready to trigger. And I'm going to do an open loop on here, and I've got my resistor set to 50 ohms on my RLC circuit. All right, so it's triggered. It's going to take about 10 seconds to display it, and you can see here it has very little resistance. You see the yellow is the step response. So we go down from 0 up to 5 volts. The yellow is immediate because we're doing no control. We're just outputting. We're saying we were at 0. When I flipped the switch, it went to 5 volts. The blue is the charging of the capacitor. Now again, I had the switch set at 50 ohms, so it charged very, very quickly because there was little resistance. I'm now going to flip the switch into the 1K, and I'm going to run it again, but I'm using a 1K ohm resistor instead of a 50 ohm resistor. And so I trigger it, and it's collecting the data now, and what you're going to see how long it's taking to charge. That's because it's a 1,000 ohm compared to 50 ohm, so it's taking a long time for that capacitor to charge up. Okay, that is open loop. Both of these are open loop with the 2 different resistors. Now I'm going to go ahead and leave the resistor in the 1K position but I'm going to close the loop, but put just a little bit of gain on here. And so I'm going to energize my capacitor again, and I'm going to do closed loop proportional gain with a gain of 1/2. So if you notice here, right, the gain is 1/2 because I have it set on the lowest position. And so you can see now that the gain, it actually was really high and then it came down. But the other thing you notice, right, is it's not going to 5 volts. It's only going to about 1.5 volts. And that is what we call the steady state error, right? My set point is still 5 volts, but I didn't get anywhere near that. With a gain of 1/2, I have a huge steady state error. My signal should be way up here at 5 volts like it was with the open loop. Go back and look at the open loop. But so I have this huge steady state error. All right, and the system was really slow, but it was faster. It actually came up to this final value, even though the final value wasn't anything near what it was before, but it actually came up to that final value much faster than an open loop. So we sped up the system, but now we have some huge error. So what I'm going to do is I'm going to increase my gain to 1, and I'm going to hit set again. And actually, I forgot to flip the switch back to 0, so that's it's discharging. I'm going to re-energize my scope. And now I'm going to energize this. So this is with a gain of 1. So I doubled my gain. So you notice how now it jumps way up here to 5, but then it drops down. So the system responded faster. But and it has less steady state error, because remember, it's supposed to be all the way up here at 5, and it's not. Okay, it's still at maybe 2.5 or so. So there's still quite a bit of steady state error in here, but less error than we had before. So we increased the gain. We got our control signal was much higher. It went all the way up to 5. It didn't go up that high before. And the system responded faster, and I have less steady state error, but I still have steady state error. I should be up here at 5. All right, so I'm going to increase my gain now to 2. So my gain is now 2. I flipped the switch to 2, and I'm going to hit it again and capture this response. And you see now the gain, or the control signal, went off the scope because it actually went all the way up to 10. So I've actually got to I actually have to change the scaling for my control signal. It was so large. So you see it stays 10 for a long time, and then it starts coming back down. Okay, now remember, it actually is coming down to my steady state value here in this case to hold the capacitor at that voltage. But again, the capacitor should be at 5 volts. Okay, so it should be at 5 volts, so it's still only at about 3.3 volts. So I still have steady state error. All right, so finally here I'm going to kick it all the way up to 5 and try it again. So I'm going to flip. Now my gain is at 5, which is the highest gain that I've got on here right now. And I'm going to energize the control signal once again. Okay, and now you see that I actually have some overshoot. You see the blue actually went above the final value. Although notice it still hasn't broke 5 volts, right? Let me just turn the amplitude cursor on here for a minute. Okay, so right here is the 5 volt setting. This is where it should be going. And it's not going that high. Okay, but so I still have steady state error. Anytime you do proportional control, I guarantee you're going to have some steady state error. You're not going to go to your set point. All right, so you're going to have to do something else to get rid of that error completely. But I did reduce the error. All right, but now you see that it's overshooting that final value, and then it comes back. So this little hump here above that line, if I adjust my cursor down here, okay, you can see that the blue is going above that final value of where it ends. That's what we call overshoot. The yellow is the control system. Now look how long the yellow is going up to 10, and it can't go beyond 10 because the control system can't go beyond 10. So you got to also consider your limitations on your control system. So it can't go beyond 10, and so it just stays 10 for a very long time. Okay, now notice I've changed this to 2 volts, so the yellow is at 10 volts there. 2 volts per division. 2, 4, 6, 8. I guess it's actually just going to 8 volts right now and staying there. So the control system could actually go more than that, but it's not. The controller is telling it not to go beyond that. Okay, and so but it's staying there for a while, and then once it sees that, you see right there, once the output gets above that final value, then it ends up dropping back down and trying to push the system back down, and then it's like, whoops, I pushed it too low and I need to push it back up. So you can see that's why it's bouncing around. So again, this is on the 1 volt, and you can see it's cut off at the top here, but you can see how once we reach, we're already kind of bringing the control system back down, and we're trying to push it back down because we know we overshot, and then we go under, we push it too low, we go under, all right, and we get these oscillations. So this will happen when you start increasing your gain. So the more you increase your gain, the more oscillations you can add into the system, and the more overshoot you can have.